In this section, we are going to study three complex reaction mechanisms: the gas phase unimolecular reactions, polymerization kinetics, enzyme catalyzed reactions. It is well known that many gas reactions follow the first-order reaction. An example is cyclopropane and propene undergo isomization reaction follows the first-order reaction, or unimolecular reaction. In theory, molecules need to collide to acquire enough energy to react, but the collision are bimolecular events, not unimolecular. So how do we explain this gas phase reaction follow first order or unimolecular reaction? One successful theory to explain gas phase reaction is Lindemann-Hinshelwood mechanism. In Lindemann-Hinshelwood mechanism, two gas molecules first collide with each other, and one of the two molecules gain enough energy to become an activated molecule. This activated molecule forms the product. All right. So here is how we write the elementary steps. So in elementary steps, the first step is two molecules A collide. One of these two molecules becomes an activated high-energy molecule. The star means it's activated, and the other is non-activated. So the rate constant for the forward reaction is Ka. Now this activated high-energy molecule can also collide with another molecule to lose energy, go back to the two regular molecules. Now, more importantly, this activated molecule can produce the product, and that's the second step. Okay, let's write the rate law for the overall reaction. So if we choose the product, all right, only the second step involves product. So we can write dP, okay, the product change with time. The rate law is the second step, should be the rate constant times reactants should be the A star. Okay, note that the reactants is an intermediate. The activated molecule is not a reactant nor product, it's an intermediate, shouldn't be included in the final rate law. Therefore, we need a steady state approximation to find this concentration. All right, so we look at the first step. So the first step, forward reaction produce the intermediate. So it should be Ka, the rate constant times reactants have 2. It's bimolecular, so it's A squared. All right, so it's Ka times A squared. That's the forward rate law to produce intermediate. The reverse reaction consumes A star, and therefore it's a negative sign. And the reaction is also second order because it's a bimolecular reaction. You have A star, you also have A, and that's why you have Ka prime times A star. Okay, you have a negative sign. All right, now the second step also involves the intermediate. It consumes the intermediate, and therefore the rate law should be negative. It consumes intermediate, negative Kb times A star. So the total reaction rate for the intermediate is you combine these three together. So the forward, all right, the reverse, and the second step. All right, the steady state approximation tells us that this rate for the intermediate should be 0. All right, the concentration shouldn't change of the intermediate. All right, so by doing that, we can calculate the intermediate concentration. So we can factor out. So this equation becomes Ka A squared minus factor this concentration, the intermediate concentration, and then Ka prime plus Kb equals 0. And therefore, this one should equals to Ka times A star squared divided by Ka plus times A plus Kb. All right, so now we have the intermediate concentration. We just plug in the rate law for product, and the final result is this rate law. Okay, so that's the rate law under Lindemann-Hinschulte mechanism. Under steady-state approximation, Lindemann-Hinschulte mechanism leads to this rate law that is neither first-order nor second-order reaction. However, if the system is under high pressure, okay, so high pressure gas molecules, the concentration A times Ka prime may be much greater than Kb. So if Kb becomes small, then in the rate law, Kb can be omitted, and the rate law becomes Ka Kb A squared divided by Ka prime A. And A squared divided by A give you 1A. And therefore, the rate law now becomes a first-order reaction. And the rate constant is the combination of Ka Kb divided by Ka prime. Now, at high pressure, when Ka times A, Ka prime times A is much greater than Kb, so Kb is small, that indicates the second step is slow, and this is the rate determining step. Note that the second step is a unimolecular reaction. All right, so this explains, okay, the reaction is first order. Okay, unimolecular reaction determines leads to first order reaction. On the other hand, when the pressure is low, all right, then Ka prime times A may be smaller than Kb. So in this case, the rate law Ka prime times A can be omitted, because that's a small number, and therefore this leads to a second order reaction. Okay, so when the Ka prime times A is smaller than Kb, that means the first step is slow, which is a rate determining step. But the first step is unimolecular reaction, is a bimolecular reaction, and therefore that explains the reaction becomes a second order reaction. So Lindemann-Hinschulte mechanism predict that gas phase reaction should go from second order to first order as the pressure increase. And this is confirmed by experiments. So this becomes a very common gas reaction mechanism as the collisions supply energy for the reaction to proceed. At high pressure, Lindemann-Hinschulte mechanism leads to a first-order reaction, and the rate constant is a combination of Ka, Kb, Ka prime. By applying the Arrhenius equation, okay, we can find the total reaction, the activation energy. So combine. So this is the Arrhenius equation for the first step, and this is for the second step, and this is for the reverse reaction Ka prime. So combine all A constant together, and the power added together when they multiply minus this one when you divide by the exponential, so you have this equation, and this combination of E give you the new activation energy EA, and so this is the total activation energy, which equals the first step, second step minus the reverse step for the first step. All right, and you have seen this in the last chapter. In order to quantitatively test Lindemann-Hinschulte mechanism, we can assume this reaction is a first-order reaction. So we can rewrite as Ka Kb times A divided by Ka prime A plus Kb times A. So the square, you times this, okay, you separate them. So if you combine all these together and say this is the effective rate constant, then the reaction is first order times A. But the Kr, which the effective rate constant, is actually a function of concentration. Okay, now we can inverse this equation. So the left side becomes 1 over Kr, and the right side you have first term, which is a combination of the 3 rate constant, and the right side is 1 over Ka 1 over A. Okay, so A is a variable. The concentration depends on the pressure of the gas reaction, okay, gas system. So if we can measure the effective rate constant as a function of A, then this equation suggests that the 1 over Kr, 1 over A is a linear relation. Okay, so if you plot 1 over Kr, 1 over A, all right, you should get a straight line according to linear Lindemann-Hinschulte mechanism. And experiments show that at high pressure, okay, the experimental data matches theory very well. But when the pressure goes low, they start to deviate from the curve. And therefore, that indicates that some improvement is needed for Lindemann-Hinschulte mechanism at low pressure. Example, at 300 Kelvin, the gas phase reaction AP follows Lindemann-Hinschulte mechanism, and the effective rate constant can be measured so at two different concentrations. So at the concentration A1, the effective rate constant is this one measured, and at a different concentration and different effective rate constant is measured. So the question is, what is the rate constant for Ka? Okay, so Ka is called activation step. So if you remember, the Lindemann-Hinschulte mechanism says the first step is two molecules collide, all right, forms activated molecule plus A, and the active molecules may go back to the unactivated molecule, and the A active molecule may also go to the product. Okay, so the first step, okay, Ka, this is the called the activation step, because this step forms the activated molecule, and therefore we want to calculate the Ka. Okay, so Lindemann-Hinschulte mechanism says that the effective rate constant, okay, is a function of concentration. So we can, if we measure different concentration, different activation, the rate constant, we can write two different equations. So one is Kr1. So that's when the pressure or concentration is A1. Now this constant, rate constant, doesn't change. So Ka Kb plus 1 over Ka when the concentration is 1. So A1, when the concentration is 1, the effective rate constant is Kr1. All right. If you now change to different concentration and you measure, the rate constant is 1 over Kr2, and this doesn't change, Ka Kb. All right. So 1 over Ka A2. So this is A2, and combine these two equations, and this is 1, this is 2. So if you use 2 minus 1, then all these constants cancel each other. So now you see you only have Ka left, and that's the effective, the activation step rate constant. That's the one we want to calculate. So what we have now is this equation. So 1 over Kr2 minus 1 over Kr1. So this is 1 equals 1 over Ka times 1 over A2 minus 1 over A1. So plugging all the data that are given, so we can calculate Ka. The activation step Ka is 4.72 cubic decimeter per mole per second. We have studied gas phase reaction mechanisms. Now let's look at polymerization kinetics. Two common polymerization kinetics are stepwise polymerization, chain polymerization. In stepwise polymerization, growth can start at any pair of monomer, new chain begin to form throughout a reaction. Average molar mass grows linearly with time. In chain polymerization, only the activated site at the end of the growing chain react to the monomers, and average molar mass doesn't change with time. The yield of the polymer increases with time. Here shows an example of stepwise polymerization. And when a carboxylic acid group A reacts with a hydroxide group in alcohol B, it will lose water and forms an ester. Okay, so this is an ester functional group. Now, if original acid, carboxylic acid has two carboxylic group and the alcohol has two hydroxide, then the product ester still have a hydroxide and a carboxylic acid group, and these two functional groups can still react. So, for example, the alcohol hydroxide on the right side react with another carboxylic acid A molecule, OH. Okay, so the hydroxy carboxylic acid forms as the ester functional group, and the left side carboxylic acid group can react with another B molecule, so OH. Okay, and that will react to form another ester. So it's just keep reacting with neighboring molecules. The molecules becomes longer and longer and leads to a polymer. So in this case, it's called a polyester. Stepwise reactions are usually second order reaction because the reaction is between two molecules. Since stepwise polymerization is a second order reaction, the integral rate law follows second order. And let's define P as the fraction of functional groups that have condensed at time t. So P is initial concentration of functional group minus the functional group left. Okay, so this gives you how much reacted divided by initial concentration, and so that's fraction that is reacted or condensed. Okay, so if we plug in the integral rate law, all right, we can get a equation tells us the fraction of the functional group condensed as a function of time. Okay, now this equation can also be modified to show that the concentration left is a function of P. The degree of polymerization is defined as the average number of monomer residues per polymer molecule, and it tells you how many monomers in a polymer chain. And it is calculated by initial concentration divided by the concentration at a certain time. For example, if you start with 10 monomers, and at a certain time, there's 2 molecules. So each molecule has 5 monomers. Okay. Now, last slide, we showed that the concentration is related to the P. Okay, P is the fraction of the molecules condensed. Okay, so plug in. So we have this equation. Okay, and if we plot, so this is the degree of polymerization, or the polymer chain length is the length of polymer, and this is the fraction condensed, the P. All right, you can see that for a large condensed fraction condensed, even for 50 or 60% of functional group condensed, the length is still low. Okay, small length. The reason is in stepwise polymerization, the polymerization can happen at any molecules. So here A polymerize with B, A, B, but at the another site, A, B can still happen. All right, and here also happen. All right, so the monomers grow at any place between 2 molecules. Only when the fraction condensed is high, for example, 80, above 80, All right. Then in the solution, the monomer, there's not a lot of monomers left, and then these start to react. Okay, so the chain start to grow long, suddenly grows, increase, okay, rise in a large number. All right. Now we can also use integral rate law as a function of time, concentration as a function of time. Then we can calculate the degree of polymerization as a function of time, and it shows that the function, the degree of polymerization increases with time linearly, and so the average length grows linearly with time. The longer the stepwise polymerization proceeds, the higher the average molar mass. Okay, if you want to grow longer chain, you should leave it for a long time. Example: consider a polymer formed by stepwise process with a rate constant given and an initial monomer concentration given. What is the degree of polymerization and the fraction condensed P at time 1.5 times 10 to the 4th power seconds? Okay, so last slide we have equation relates degree of polymerization with time linearly. So plug in, so this is initial concentration, all right, and this is the time. So plug in easily, you can find it's 61. So at this time, in average, each chain has 61 monomers. The P, we have another equation, N is 1 over 1 minus P. So N already calculated, so P can be calculated. So the fraction condensed is about 98%, is 0.98. Chain polymerization involves radicals. The first step usually requires an initiator, and one example is a peroxide, where there's a weak oxygen-oxygen bond. This bond breaks under heat, forms a radical, and the radical attack a monomer, forms a new radical, and this is called the initiation step. The radical formed by the monomer now can attack another monomer, forms a larger radical, and this larger radical attack another monomer, forms even larger radical. So this repeats itself. The radicals grow in length. So compare with stepwise polymerization. In stepwise polymerization, the reaction can happen between any two molecules. In chain polymerization, one of the reactants has to be a radical. The radical chain polymerization mechanism involves 3 steps. In the initiation step, an initiator forms a radical, and the radical combined with a monomer forms an activated monomer, which is also a radical. In propagation step, the radical formed by the monomer now can react with another monomer to form a larger molecule. The reaction repeats and the radical grows in length. In the termination step, 2 radicals combine, lose unpaired electron, the reaction stops. Let's look at the kinetics of radical chain polymerization. The initiation step is the step to form radicals, and the rate determining step is the first step. The initiator forms 2 radicals, and it's a unimolecular reaction, so it's a first order reaction. The rate law is Ki, I means initiation step, times I. Okay, that's the rate law. Now because it forms 2 radicals, you need to times 2 for the radical concentration change. And not all these radicals formed that will initiate the monomers, and there's a fraction, so you times F, which represents the fraction of the molecules that will initiate radical formation. Okay, so that's the rate law for the initiation step. For propagation step, this step forms grow polymer, and this reaction is a bimolecular reaction, so it's a second order. Kp times M is a monomer, Mi is a radical. And in termination step, 2 radicals consumed to form a larger molecule. So it's a second order. Because it consumes radical, so we have a negative sign. All right, so negative sign times 2 because 2 of them consumed. And also it's a second order, all right, because of bimolecular reaction. All right, note that initiation step forms radical, termination step consumes radical. So these 2 steps changes radical concentration. In propagation step, the concentration of radical doesn't change. The radical just grow longer. Here are the rate laws for the initiation step, propagation step, termination step. Under steady state approximation, the concentration of radical should be constant. In other words, the radical formation from initiation step should equal to the radical consumption in the termination step. So in other words, whenever you form a new radical, a old radical combine forms a final polymer. Okay, so combine these 2 radical formation consumption rate equals 0, and that gives you the radical concentration under steady state approximation. And this, using this concentration, put into the propagation reaction rate, and we can calculate the rate of polymerization. All right, so this is the rate of polymerization, which is the first order with monomer, okay, and the half order with initiator. So both are important. The monomer and the initiator will affect the reaction rate, the polymerization rate. So the rate of polymerization is proportional to the square root of the initiator concentration. The kinetic chain length is defined as the rate of propagation of chains divided by rate of production of chains. The radical concentration can be calculated using steady state approximation. Plug into this equation, we can calculate the kinetic chain length. Note that the rate of propagation is half order with respect to I, but the formation rate is first order. So this gives you negative half order for initiator. So first order with monomer, negative half order with I. Okay. Now, if 2 radicals combine forms a in a termination step to form a polymer, then the average chain length for a polymer should be twice this kinetic chain length. Again, this shows that the polymer length is proportional to the monomer, but inversely proportional to the square root of initiator. So if you want to make a longer chain, you don't want too many initiators. Maybe smaller amount is good to make a chain longer chain length. Okay, you still need an initiator to initiate the reaction, but the more chain initiator you have, the smaller the final radical length. Here is a comparison of stepwise versus chain polymerization. In stepwise growth, the reaction can take place between any 2 monomers. So at the beginning, many small polymers may form, and the length increase with time. On the other hand, in chain polymerization, the reaction must involve a radical, and so in a short time, the radical can reach the final chain length, and with time the length doesn't change. What changes is the yield. So with time, more and more polymer will form. In kinetics, catalyst plays a very important role. A catalyst is a substance that increases the rate of reaction without being consumed. Okay, this is very important because many factors can affect the reaction rate, but only catalyst that can change rate without being consumed in the overall reaction. Now, usually we use this energy diagram to show the effect of catalyst. So a reactants usually go through a transition state, forms the product, and this energy barrier is the catalyst, is the activation energy. Now, a catalyst can participate in the reaction and combine with the reactants, and it goes through a different path. So this is the path with the catalyst, and this path has lower activation energy. So catalyst can lower the activation energy, go through a different path to form the product. Usually, the reaction in the reaction mechanism, in the catalyst react with reactants, forms intermediate, and then forms product. It will be regenerated, and that's also an important characteristic. Catalyst can be regenerated, and that's why it's not consumed in the overall reaction. Now, there are several types of catalyst. One is called homogeneous catalyst, and this catalyst is in the same phase as the reactants and the mixture, reactants or product. So one example is acid-base catalysis. And in industry, most catalysts are heterogeneous catalysts. And these catalysts are in different phases with reactants or products. One example is ammonia synthesis. So nitrogen gas, hydrogen gas forms ammonia gas. So these are all gases, but catalyst is a solid ion. The advantage of heterogeneous catalyst is that the catalyst can be easily separated from the reactants or the product because they are in the different phases. Also, look at the energy diagram. Catalysts change the reaction path to reduce activation energy, but it does not change the energy of reactants nor the energy of the product. In other words, it can affect kinetic to change reaction rate, but not thermodynamics, the equilibrium constant. Here is an example of homogeneous catalysis. Hydrogen peroxide decomposes into water and oxygen. This reaction does not happen in a significant amount, but when bromide is added, the hydrogen peroxide decomposes quickly. So here is a mechanism, and which involves 3 steps. In the first step, hydrogen peroxide reacts with acid, which is protonated, and so protonated hydrogen peroxide. The hydrogen peroxide, the protonated hydrogen peroxide reacts with bromide, forms an intermediate HOBr. This intermediate reacts with another hydrogen peroxide, give back bromide and the hydrogen ion and oxygen gas. Now, in this mechanism, the first step is fast, so it reaches equilibrium. And we can write equilibrium constant, and we can calculate the intermediate, the protonated hydrogen peroxide concentration. And the second step is a slow step, and therefore this is the rate determining step. And the reaction rate is second order. Okay, so we can see that in this reaction, bromide as a catalyst participate in the reaction, but in the last step it is regenerated. So overall, in the overall reaction, bromide does not appear in the overall reaction. Okay, it's consumed but also regenerated. All right, and the rate law, because this second step is the slowest step, and therefore the overall rate law should be equal to the second step rate law, which is K times hydrogen, the protonated hydrogen peroxide times bromide. Now this activated hydrogen peroxide can be calculated using equilibrium constant. So if we plug in everything, and we can show that the overall rate law is proportional to the reactants, hydrogen peroxide, but also proportional to the acid concentration and the bromide. So it's very common that catalyst does not appear in the overall reaction, but it is in the rate law. It affects the reaction rate law. One example of homogeneous catalysis is enzyme catalysis. Enzymes are protein molecules that serve as biological catalysts. They contain active sites that can bind the substrate or the reactant. The reactants becomes activated and they forms product. Because the particular requirements of the geometry of these reactants to fit the enzyme specific active site, and this active site is specific to the reaction that is catalyzed. As usual, the catalyst or the enzyme reduce activation energy and make reaction go faster. In lock and key model, enzyme and the reactants or the substrate first combine forms enzyme substrate complex. The reactants or the substrate is activated, forms a product, and then the product leave the active sites of enzyme. The mechanism is written as the following. Enzyme react with substrate, forms enzyme substrate complex. The enzyme substrate complex, ES, may go back to enzyme and the substrate, or it can produce the product and regenerate enzyme. And this mechanism is called the Michaelis-Menten mechanism. Let's derive rate law for the enzyme catalysis. The overall reaction is simply the reactants or the substrate forms a product. Although enzyme participate in the reaction, it is regenerated, and therefore it's not consumed in the overall reaction. Now we can choose product to derive rate law, and the product only appear in a second step. All right, so the rate law is the K2 rate constant times the reactants, which is ES. Now because the ES is the enzyme substrate complex, which is the intermediate, and therefore the next step is use a steady state approximation to find the concentration of enzyme substrate complex. This is the formation rate for the product, which involves enzyme substrate complex. The steady state approximation tells us that this enzyme substrate complex should not change with time. The reaction rate is 0. From the mechanism, we can write the reaction rate for the enzyme substrate complex. The first step, forward reaction, is a second order reaction, so K1 ES to produce enzyme. The reverse reaction is unimolecular reaction, first order, so it's K-1 ES, okay, with a negative sign. And the second step also consumes ES, so minus K2 times ES equals 0. Factor ES, so this becomes K1 ES minus ES, okay, this is the one we want to find out, okay, times K-1 plus K2 equals 0. And ES can be calculated, right, to be K1 ES E times S divided by K-1 plus K2. All right. Now, before we use this to plug into this equation, let's combine all these constants together and give a name, which is called Michaelis constant. Note that Michaelis constant is defined as the inverse of this constant. In other words, Michaelis constant is K-1 plus K2 divided by K1. So if you look at the mechanism, K1 is the formation of the ES. So it's the enzyme combined with the substrate to form ES. K-1 and K2 are both consumption of ES from ES to go back to the enzyme and the substrate or to the product. So this combined together tells you how reactive the enzyme substrate complex is, the intermediate is how reactive. And the K1, it tells you how strong the affinity of this enzyme to the substrate. So a large K Michaelis constant tells you the enzyme substrate complex is very reactive, that immediately decay into product or the reactants. And a small Km indicates the substrate has a high affinity for the enzyme. So now let's put back into, so that's the 1 over Km times Es, and put back into the rate law. So here is the rate law, okay, for this reaction, which is K2 divided by K Michaelis constant times E times S. So E is the free enzyme concentration, S is the free substrate concentration. We just derived this rate law for the enzyme catalysis. And this equation tells us that the reaction is the first order with the substrate and also first order with enzyme, the catalyst. This equation is not always convenient because the concentration of enzyme and the substrate at any instant is not easy to know. And if the reaction has not proceeded for too long or at the early stage, then the substrate concentration should be approximately the initial concentration that we added to the system. And so we can write the initial reaction rate. So this represents the reaction rate at the early stage, should equals to K2 over Km E times S naught, so the initial concentration. So this is the one we already know. We know how much added. But the enzyme, we still don't know. We know the initial enzyme, okay? But how much enzyme at a particular instant, okay, we don't know. Now, how is this related to this one? Okay, so first, at any instant, some enzyme you added forms the enzyme substrate complex, and some enzyme is still unreacted, which is a free enzyme. But they add together, okay? So the enzyme, free enzyme plus the enzyme substrate complex should equal to the initial enzyme concentration. Okay, so that's one equation. Another equation is the results from steady state approximation. The enzyme substrate complex equals 1 over Michaelis constant divided by times E times S. Okay, this equation is derived in the last 2 slides. Now combine these two equations, we can find the relation of enzyme and the initial enzyme, because this cancel each. If you add these two equations, the enzyme substrate complex will cancel each other. So we have this enzyme concentration equals initial enzyme concentration divided by 1 plus the substrate initial substrate concentration divided by Michaelis constant. So this is -1 power divided by Michaelis constant. So plug in this equation. All right. So finally, we have the rate law that we can use to calculate reaction rate at the early stage, which is K2 times E naught, the initial enzyme, S naught, initial substrate concentration, Michaelis constant plus S naught, initial substrate concentration. We derived this Michaelis-Menten equation. That is, the reaction rate is K2 times E naught times S naught divided by S naught plus Km. If we plot this reaction rate as a function of substrate concentration, we can see that at a low concentration of substrate here, the reaction rate is proportional to the substrate concentration, which indicates the reaction is the first order. If we look at the Michaelis-Menten equation, when S naught is small, and this term can be omitted, so the reaction becomes first order with S naught, first order with E naught. Now, when the concentration of substrate becomes large, the reaction rate approach a constant. Okay, so if we again look at the Michaelis-Menten equation, when S0 is very large, then Km can be omitted, and the equation becomes S0 divided by S0, so this cancel each other, so we get K2 times E0, and so this number that the reaction rate is approaching to is K2 times E0. Okay, and because the reaction rate approach this number, and this is called the maximum reaction rate, so K2 times E0 is the maximum reaction rate that this system can approach when the enzyme concentration is fixed, and this can be approached when the concentration of substrate is high enough. You have high concentration, all right, very high concentration. The reaction rate will approach this number K2 E0. That's called the maximum Vmx. Okay, and therefore the Michaelis-Menten equation can rewritten as a fraction times Vmx. Okay, because K2 times E0 is the Vmx. So here is the conclusion. The reaction, if enzyme concentration is fixed, the maximum reaction rate the system can approach is K2 times E0. If the concentration of the substrate is not high, then the reaction rate should use Vmx times a fraction that involves substrate concentration. It is S0 divided by S0 plus K Michaelis constant, then times Vmx. In order to determine the Michaelis constant and the Vmx experimentally, we inverse this Michaelis-Menten equation. So the left side becomes 1 over V0, and the right side becomes S0 plus Michaelis constant divided by S0 times 1 over Vmx. Okay, so S0 divided by S0 is 1. So the first one, so this becomes 1 over Vmx plus, and Km divided by S0 times 1 over Vmx, we can write as Km divided by Vmx times 1 over S0. All right, so this gives you this equation. So the left side is 1 over V0, right side 1 over Vmx plus Michaelis constant divided by Vmx times 1 over S0. Now this equation reminds us a linear equation where y equals b plus kx. Okay, so here y is 1 over V0 and x is 1 over S0. Okay, S0 is a variable, so 1 over S0, and b is this 1 over Vmx, and this is the slope k. Okay, so here is a plot. All right, so if we plot 1 over reaction rate and the x is 1 over S0, we should get a straight line. Okay, the straight line, the slope is Km over Vmx. The interception with y is 1 over Vmx. Okay, now if we know enzyme concentration, then Vmx is just K2 times enzyme concentration. So K2 can be calculated. So using this Vmx, okay, plug into the slope, we can find the Michaelis constant. In enzyme catalysis, turnover frequency, or catalytic constant kcat, is defined as the maximum number of catalytic cycles or turnovers performed by a single enzyme molecule per unit of time. So based on this definition, kcat should equals to maximum reaction rate divided by enzyme concentration. Now the maximum reaction rate is K2 times E0. So this ratio just gives you K2, and therefore K2 in enzyme catalysis plays a very important role. It tells you the turnover frequency or catalytic constant. Another important concept is catalytic efficiency, which is kcat divided by Michaelis constant. So kcat is just K2 divided by Michaelis constant give you K1, K2 divided by K minus 1 plus K2. All right, so the maximum catalytic efficiency will be K1. Enzyme carbonic anhydrase catalyze the hydration of reaction of CO2, so this reaction. And the reaction is done with initial enzyme concentration 2.3 nanomole, so that's E0. Okay, and when we change, so this is CO2, which is substrate, which is S0, all right, and this is the reaction rate, V0. Okay, we want to find the catalytic efficiency. So we need to first find the Michaelis constant and the Vmx. Okay, to do that, we use the equation we derived in the last slide, and we need to plot 1 over V0 over 1 over S0. So on the table, we add 2 columns. So one is inverse V0, 1 over S0, and the plot 1 over V0 over 1 over S0, we get a straight line, and the intersection here is 1 over Vmx, and therefore Vmx can be calculated. Okay, and the slope is the Km over Vmx. So plug in the Vmx, Michaelis constant can be calculated, and then according to the definition, the kcat can be calculated and the efficiency can be calculated. Here shows some examples of heterogeneous catalysis. The synthesis of ammonia using iron as the catalyst. The synthesis of sulfur trioxide, which is used to make sulfuric acid, uses vanadium oxide as the catalyst. And the isomization of pentane to 2-methylbutane uses platinum as the catalyst. In all these reactions, the catalyst is a solid, and therefore the chemical reaction must occur on the surface of the solid. And the surface area is a very important parameter in heterogeneous catalysis. The heterogeneous catalysts catalyze the chemical reactions usually undergo the following steps. First, the gas molecules physically absorbed onto the surface. And these molecules undergo electron rearrangement and becomes chemically absorbed. And these molecules start to react on the surface and becomes the product, and the product leaves the surface. So the reactions undergo physical absorption, chemical absorption, reaction, and desorption. Again, the reactant molecules first physisorbed onto the surface, and then undergo dissociation, becomes chemisorbed atoms, and these atoms react to form the product, and the product leave the surface.